Today's daily LeetCode problem of the day is number of good leaf node pairs, number 1530. For this problem, we're given the root of a binary tree and an integer distance. A pair of two different leaf nodes of a binary tree is said to be good if the length of the shortest path between them is less than or equal to distance. We want to return the number of good leaf node pairs in a tree. So for this example, 4 is a leaf because it has no children, and 3 is a leaf because it has no children. So therefore, they could be a good pair as long as their distance is less than or equal to 3. 1, 2, 3, it is. So we have one good pair, 4 and 3. Let's look at this example. Distance is 3 once again. So the only good pairs are 4 and 5 and 6 and 7 because we cannot get from 5 to 6 without going more than 3. 1, 2, 3, 4. So we want to find the number of good pairs. So how are we going to do this? We're going to use a depth first search. Our depth first search is going to be a post-order traversal. This means that we're going to visit the left subtree first, then we're going to visit our right subtree. This is also going to be a recursive function. So if our node is null, we will return an empty array. So we're going to use arrays to track the distance and track our leaf nodes because arrays stay the same through recursion. So we're also going to use an array to track our result because it's not like an integer, it won't be reset when we pass it through recursion. So we're going to first check if it's null. If it's not null, then we'll check if it is a leaf node. If it is a leaf node, we will set its current position in an array. It's like graphing our tree. We'll then check the left subtree. If it is not a leaf node and we don't track its position, we will check the left subtree, then check the right subtree. Based off of what we find from those, we'll count the pair of leaf nodes found in those subtrees. We'll do that by using a loop within a loop, using our result array, and checking to make sure the positions of two leaf nodes match up in both left subtree and right subtree graphs. We'll do this by checking if 1 multiplied by another is equal to either a 0 or a 1. If it's a 1, they have a matching node. If it's a 0, they don't. After that, we'll then check the combined distance. And the combined distance is basically just updating the distance from a leaf node to whatever node we are going to recursively go back to. By checking the combined distance, we're able to update the distance we are from the leaf. If we get too far of a distance from the leaf, it will be left out of the array, which means that it's no longer in a possible area to be matched to another leaf node. So how do we implement this? First things first is let's initialize our integer array result, a new int array, and it's only going to be of length 1 because it's just going to be our output answer. We're then going to do a depth first search, and we're going to pass it our root, distance, and our result. Eventually, we're just going to return result of 0. Now for our depth first search, we're going to have a private, and it's going to return integer arrays. Those integer arrays are going to track our distance from leaf nodes. It's going to be called depth first search. It's going to receive a tree node. We can call it temp, an integer distance, and an integer array result. So, like I said, we're going to do break recursion if null, check if it's a leaf, visit left subtree, visit right subtree, count pairs of leaf nodes from subtrees, and then combine distance from left and right subtrees. Then we simply return combined distance. So let's do this. First things first, how do we break the recursion? If our temp node is null, return an empty integer array. New int, and it's going to be of distance plus 1. The reason we're doing distance plus 1, let's say, for example, distance is equal to 3, it's going to look like this. 0, 0, 0, 0. When we do find a leaf here, it's going to update this. So then this is going to be 1. When we combined our left and right subtrees and we don't find another leaf for it to match to, this will be 0, this will be updated to 1. Then we'll go through the process again, this will be 0, this will be updated to 1. We'll go through the process again, and then eventually it'll all be 0. We're no longer tracking this node because it is out of bounds. Next, we want to check if it is a leaf. So if temp.left is equal to null and temp.right is equal to null. It has no children, so it is a leaf. We're going to have an integer array, leaf distance. It's going to be a new integer of distance plus 1, like I just said, and we're going to update its first variable. So leaf distance of 1 is equal to 1. That's marking its position. We then return leaf. So the reason we're leaving this as a 0 and updating this as a 1 is because we're saying this is the leaf. So when we recursively go back to the parent node, it's going to be a distance of 1 away. Then when we go back from the parent node, we're going to be 2 away. Then we go to the parent node, then it's going to be here, and it's going to be 3 away. And then eventually it will be out of bounds for a match. Then we're going to visit our left subtree. So integer array left distance is equal to a depth first search, where we simply pass our temp.left distance and result. Now let's visit our right subtree. So integer array right dis is equal to a depth first search, temp.right distance and result. Now we want to count the pairs from the subtrees. How do we do that? It's going to be a double loop, and we're going to basically look at both the left distance and the right distance, multiply them together, and see if they either come to a 1 or to a 0. If it's a 1, we add a pair. If it's not, then we don't add a pair. So for int I is equal to 1, because that's where it will be marked first. There's never going to be a leaf marked in the 0 position. I is less than or equal to distance I plus plus. So for int j is equal to 1 as well. J is less than or equal to distance minus I, so we don't run out of bounds, j plus plus. So our result of 0 is going to plus equal the left dis of I times the right dis of j. So if that comes out to 1, it'll be added to our result. Otherwise, our result is going to be added to 0. Then we want to combine the distance from the left and right subtrees so we can update it before we go back to the parent. So our integer array combined this is going to be equal to a new integer of distance plus 1. Then another for loop. So for int I is equal to 1, the 0 position is still always 0. As long as I is less than distance, I plus plus. So the combined this is combined dist of I plus 1 is equal to the left dis of I plus the right dis of I. Then, after we update our distances, we can simply return our combined distance. So if we run this, passes our test cases, and if we submit it, passes all solutions. Let's try this in Python. So for Python, it's going to be basically the same. Let's first initiate result, and then we're going to call self dot. For search, we're passing root, distance, and result, and then we're going to return result of 0. So let's define depth first search. It's going to have the arguments self, root, distance, and result. And it's going to return a type array. So if root is equal to none, then we can return. We want to do an array of zeros times distance plus 1. Then if root dot left is equal to none and root dot right is equal to none, then we're going to have another integer array. So we're going to have leaf dis is equal to integer array full of zeros times distance plus 1, and then leaf dis of 1 will be equal to 1, and then we can return our leaf dis. Then we're going to have a left dis, which is equal to depth first search of root dot left, distance, and result, and a right dis equal to depth first search of root dot right, distance, and result. And then for I in, I'm going to say range 1 to length of distance from 1 to distance for j, oops, this should be in, for j in range of 1 to distance minus I, result of 0 will plus equal left dis times right dis of j. This should be left dis of I. Then we do combined dis equal to array of zeros times distance plus 1. So for I in range 1 to distance minus 1, combined dis of I plus 1 is equal to left dis of I plus right dis of I. Then we should be able to return combined dis. See if this works. No, it's not going to work. Oops. Sorry, it should be self dot here. So if we run this, let's see. So I updated the output to a list of integers, and I put parentheses around our definitions of the integer arrays to make sure that they are being initialized correctly. So if we run this, we're still having an issue here. So I updated the inner loop to contain from 1 until distance plus 1 minus I. So if we run this, passes our test cases, and if we submit it, passes all solutions. Thank you, and follow for more daily LeetCode solutions.